He's going to be talking to us today about Stefano.
Thank you, thank you. So yeah, I'm the community manager for OpenStack, and I consider myself, I'm hired by Rackspace, but I consider myself a little bit on the edge, facing the community and all the contributors and all the users of OpenStack. So feel free to talk bad things about Rackspace if you want to. I won't tell. I'm open. I'm the ear for reporting everything back to internally to Rackspace. So I prepared a few slides, and I will share my time with Arnold, so I will go into more details about what a part of OpenStack is. Got a few slides, but I would like for you to go home with one simple message. If I can deliver that to you, I will consider that a success. What I'm saying is, what I want you, my main thing is that OpenStack is now one of the most exciting projects that is going on. And like 20 years ago, Linux Torvalds started a little project called Linux, and it became a huge part of what we consider computing history for nowadays. OpenStack wants to be the same thing. The next 20 years, probably we will be hearing about OpenStack. It's a very exciting moment to get involved in it, because we've been going with an evolution, seeing an evolution into the data centers where we have departmental resources that have different needs, more control over the environment. As if you have heard the presentation before with John from Stanford, he was saying basically these things, that the enterprise is on a path to enabling having the cloud. And it all started with the computation nodes, the virtualization of hosts. We're introducing an abstraction layer between the servers and the hardware, basically, and the applications, where you could have better usage of each of your hardware. That was the beginning, and slowly into the enterprise, we've seen also more virtualized servers, networks, and storage. So resource pools started to be aggregated for applications in search for flexibility and efficiency as the drivers. But with the growth also came a lot of complexity, and things started to get complicated with applications that are not aware of the cloud. The VMs started to be scattered all around and was difficult to manage. So the need for a cloud operating system is now evident. So the OpenStack is the cloud operating system that I'm referring to, that allows on the top part to have applications that connect to the operating system with the APIs, users and administrators that can self-service their needs, and at the bottom, automation that makes everything more simple to manage. And so now we are there. I mean, we have this operating system, we have the tools, and we want to go forward. We want to move it to the next step, where enterprise private clouds can run their operating systems, but also public cloud run on the same operating system, so that there is interoperability, because that's what we want. We want to be able to move to have clouds, private clouds, where you run your applications in your data centers, replicated into another data center where you have, for example, disaster recovery, but also you can enable public cloud if you need to move your loads between public and private if you need to. So I have a federation of clouds that will make your life easier. So OpenStack is a community of open source developers at the moment, with organizations and users that are building this huge open source operating system. And it came out from the needs of two big companies, organizations, I should say, NASA and Rackspace, that had about over a year ago, June 2010, they put their efforts together to design to design the ubiquitous open source cloud computing platform with a very specific design in mind, something that would be simple to implement and massively scalable. And with that design in mind, the OpenStack project started with an Apache license that is very implements the openness and in the intention of the project. There is a very liberal copyright agreement. You, as a contributor, every contributor keeps copyright of the contribution. There is a very open design process where every 6 months anybody that wants to contribute discusses using blueprints, discusses the new features and whatever needs to be included in the project with the tech leads that are already in the community. And the tech leads are elected democratically with an open process. And the development is also driven completely in the open. All the branches are on Launchpad and GitHub. There is no gated, well, there are gated trunks, but there is no secret features included. There are lots of pieces at the moment. When you think of OpenStack, there are pieces that sub-projects for the computation. There's called Nova, Swift, which Joe will mention more into details, for the object storage, and slowly these were the two initial founding projects of OpenStack. Image service network and dashboard and identity have been added recently in the new release. So the project is about a year and a few months old, and we already been through 4 releases. Diablo was released in September with a lot of new features like storage as a service, networking as a service, and the unified authentication layer called Keystone. The next release is scheduled for March 2012. We have 6 months fixed time release cycles. Every release cycle is concluded with a design summit where all the developers meet in the same room. We met in Boston at the beginning of the month of September. We had 3 days long meetings and sessions with all the developers to discuss the new features, to lay down the foundation for the next release cycle. And the result is that the next release called X6 will focus on stability and on lots of operational improvements, because we're starting to have, OpenStack is starting to have big installations, big customers running it in real life, and it's not a toy, and therefore we cannot, we need to focus on these features for the next release. The community is huge. There are about 160 companies listed on the website, and this is just a selection of their logos. It's probably not totally up to date. You can see Korea Telecom that spoke. SUSE is missing, but they announced it a few days ago. Their support for OpenStack. There's Canonical, and a lot of these companies like Rackspace and Primus, they're betting their existence on OpenStack. It's a big effort, and it's a big investment for all of them, for most of them. There are 1,200 active participants around the mailing list. At the Design Summit, we had 17 countries represented. Last time I checked, only on our server, the downloads were 40,000, with 1,700 visits a day only to the documentation website, which is huge. And it's open for participation. Anybody that is interested. These are some of the contact points that we have: the mailing list, the website, Twitter, and the planet. And of course, being an open source project with so much open discussion, all the channel, the official meetings are held on IRC Freenode OpenStack. So this is what we're setting the foundation for the next generation of computing, and it's an extremely exciting space to be in. With this, I would like to save time for Joe to talk about Swift, and for questions, we'll have time afterwards.
Yeah, that sounds good. All right, thanks, Stefano. Hi, my name is Joe Arnold, and we're going to talk about OpenStack Swift. And OpenStack Swift is an object storage system that is part of OpenStack. So there's many projects of OpenStack. Swift is one of them, and it's an object storage system. So over the past year, I've done several petabytes of deployment of Swift for a couple of clients, Korea Telecom being one of them. And let's go over it. So today we're going to talk about the uses of Swift. Then I'm going to dive into why this is a storage system that people are turning to, do a brief overview of the architecture, and then just outline an example deployment. Let's jump in. So as Stefano said, OpenStack is a bunch of different projects. And in the beginning, NASA came along and contributed the compute side of OpenStack. And Rackspace came along and contributed their object storage system, which is called Cloud Files. That was awfully convenient because it was already running in production for about a year at that point. And they were running tens of thousands of customers, billions of objects in the system, and had many, many petabytes of storage. So it was something that was already production grade, and that was just, boom, released into the open source. So just to baseline what Swift is, it's a storage system that's similar to Amazon S3, if you're familiar with that. And what it is you access it via an HTTP API. And what Swift is that you can now have an Amazon S3-like deployment, and you can install that on-premise for a private cloud deployment. So backend systems can fetch and retrieve data from Swift over this API. Or you don't need to have any servers at all. You can just dish out data directly to end user applications. And that's a very common workload that we're seeing, where there's a mobile device, and instead of going through a server to fetch the data just talks directly to a Swift cluster. So it has an endpoint. Or you can hoist it up easily into a CDN. It's HTTP. So what this means is that it's not blocks. It's not a file system. It's not any of those things. It's more of a web addressable asset appliance that can be used for unstructured data. And actually, that's what's driven a lot of the adoption, has been the fact that it is an API, a web API, and for developers, it's more convenient than file systems at times. And I was able to witness this firsthand at a managed hosting site where we were doing Ruby on Rails applications, and we moved everyone over to Amazon and required them to use S3 rather than a clustered file system that we were providing. And because the client libraries had gotten so good and integrated into development platforms, no one really cared, and we were worried about it. So now that Rackspace released their cloud files into Swift, there's a lot of client library support to make adoption easy for the developers. So the fact that it's not a file system is compensated by the client libraries that target very specific languages. So I'm going to say something here that's maybe it's not 100% accurate, but I'm going to just say it just to kind of make a point. There's data sets that care about dollar per IOPS, and where performance is really important. And then there's another class of data where maybe something called long tail data, which really dollar per gigabyte is more important. So this is that second tier or even third tier or tape level storage. So the long tail storage has got to be cost effective. Nowadays, web addressable objects are really important and really convenient for application developers to use. And the system's got to be able to handle a high degree of concurrency. So lots of many simultaneous connections, and not just for service provider workloads like what they're seeing at Rackspace and at Korea Telecom, but also for popular websites that need to serve lots of simultaneous connections, reads and writes at the same time. So this, like the snapshot into my worldview with Korea Telecom, what we did was we had Nexena was for running VMs. It was in rack, ran databases. It was its own tier of primary storage. But then for application assets, we used OpenStack-Swift. And so one of the first applications that KT wanted to move to their cloud system was, there was an e-book store for digital readers, and then there was another one which was a Korea local mapping application. And so tile data, right? There's lots of that. And so there's different workloads that are on each. So, to extend that further, you would have a database which you really do care about I/O. And so that would be transactional workloads, like to take orders, update account records. It's really important to figure out how many transactions you can cram into that thing, because that's going to be a limit on how many orders you can take. Whereas the documents, the things like the tile data, the book content, that's being streamed to many end user devices, and so there's a different workload. So Swift is really good on the high concurrent, relatively low per stream I/O workloads. One of the other features is to be able to have a huge flat namespace. And so what this means is you could have like a URL, storage.mycompanyname.com, and that namespace can grow to be very large, multiple petabytes. For public clouds, you can kind of read into that as it's really good at supporting multi-tenancy. You can put a lot of users, and you can still have one addressable namespace. And then for private clouds, what it means is you can decouple applications from infrastructure, decouple teams from infrastructure. And where we're seeing private deployments use this is installing one big organization-wide cluster and then putting teams on it. So they're only maintaining one piece of infrastructure and treating that as a storage as a service platform for unstructured object data. All right, this is going to be the speed version of the infrastructure of the overview of the architecture of Swift. So hold on and catch me after the break. Three primary entities are the proxy servers, something called the ring, and zones. The proxy server takes an incoming request and forwards it on to an appropriate storage server. So there's many front-end web servers, and there's many storage nodes. And a proxy server is, think of it like a web server for, well, it is a web server for the storage system. And the overall architecture of Swift is that has pretty good linear growth scaling characteristics. So if you want more storage, you can add storage. If you need more front-end serving capacity, you can add more proxy server nodes. You need more networking bandwidth, you add fatter pipes, for example. And so the proxy server is part of this, and it's a shared nothing data structure that enables the proxy load to handle any incoming request. So there's no central brain. Any proxy node can handle any incoming request. And what makes that happen is this thing called the ring, which is a data structure that maps a URL, a URI, to a physical location on disk, or 3 physical locations on a disk. And for each object in the system, there are 3 replicas that are stored for each object. Then there's something called storage zones. And what zones are is they're isolated failure boundaries. And so unlike RAID systems, data isn't chopped up and distributed throughout the system. Whole files are distributed throughout the system, and each copy of the data lives inside of a different system. Okay? So the standard configuration is to have data distributed across 3 zones. And so initially we were thinking, hey, why don't we just have 3 zones? There's 3 copies of data, 3 zones, but what would happen is if one of the zones were to catastrophically fail or become unavailable, then there would only be 2 copies left. So there needs to be more than 3 zones if you're going to guarantee that you have 3 copies of the data. 5 is kind of nice to have, at least 5 zones, because then at least 2 of those zones can fail, and assuming there's enough room, data can replicate across. Zones can be thought of, so they're fault-tolerant domains. So what it really breaks down to is for large deployments, you have a 1 rack per zone. And if you're going to scale that down, you have 1 physical server per zone. And you can even get into smaller deployments where you have, say, 1 to 2 to 3 nodes. And what you can do is just, what's the logical fault-tolerant domain? Maybe it's a controller card, or maybe it's a grouping of drives. And you can just anoint those as zones. So you can scale it down to tens of terabytes if you thinking of starting small and growing. When a write occurs, it's a quorum. This is kind of an interesting property. So data comes in, the proxy server streams that data to 3 locations all at the same time. And 2 out of 3 must succeed. If it doesn't, if 1 succeeds, it tells the client, hey, no good. And with writes, on the way up, it reads it from 1 location. Right? This is different. So when you write, you're writing in single stream I/O to each of the disks. It's not breaking things up. So what this workload is really good for is because the I/O cost is spread across many spindles, many machines, many CPUs, a lot of RAM. Getting the high data rates out of the system must be done with a high degree of concurrency, or many simultaneous readers and writers in the system. So the trade-off here, right, is that Swift is going to have significant per access I/O latency, but in exchange for that, you get many concurrent connections capable at the same time. So you can scale that out very horizontally, very wide. So that's the trade-off. It's great for some workloads, and obviously it's not good for some others. So during a failure, every location on the ring has a pseudo-random location, a well-defined next place that data is going to live. And so when data becomes inaccessible, data is migrated to that new location, and when it's repaired, then that data is offloaded and to free up the space. So it actually works pretty well in practice. Embarrassingly, we had a client where one of the zones, at this point it was a node, was completely out, and there was no customer visible effect on that. We only noticed because when we ran a performance benchmark, it was slightly lower than what we had seen the previous time we ran it. So it was kind of neat. It's a very, very durable system. I've never felt so comfortable powering down systems to do upgrades as I have with a system like this. Yeah?
Once you migrate it to that new third location, you don't have to reproduce it back, do you? Because you've got that new location.
Well, that's a good question, and it would probably be a good optimization. But the trade-off here is how the system achieves a shared nothing system. So that lookup is really cheap, and it's consistent. So this hash string is distributed to every single node on the cluster. And that way, there really isn't a central brain that needs to know how to make the decision. And so it would be cool if you could, just redistribute that ring around. Hey, this piece of data is now living over here. But that means you have to update that ring file and redistribute it everywhere. So it's kind of a trade-off in the design, I would say. Yes, I think that would be a cool optimization to do, but that's not the way it works today. Good question. So just briefly, some example deployments. We're running these we've run it on, of course, with KT. They're using Quanta gear, but it was pretty much identical configuration as what you'd see. Here's the 4U super micro chassis, 24 to 36 disk. I hate to call them JBODs, and I hate to call them JBODs because they have decent price performance CPUs. And they're running a lot of stuff on these things. We pack them full with 24, 48 gigabytes of RAM. So they're kind of beefy machines. Interestingly, there's no RAID. The system's managing each drive individually. In fact, we're using desktop drives. Kind of irritatingly to some vendors who refuse to sell to us because of that. So that's the current sweet spot we're seeing now is 2 terabyte disks. We might use enterprise in places where we don't have that good of physical access, or remote hands aren't that good. But desktop drives elsewhere. We're seeing now people opting for 3 terabyte drives for this type of system. They're now just entering in that sweet pricing point. So it's always changing. And the system accommodates for that. So you can weight different systems according to how big they are, and the system will adapt. So 100 terabyte deployment. That might look like 2 proxy servers that are load balanced. Go with 4 zones. With 4 zones, each node is a zone with 36 disks, running 3 terabyte drives. All right.
Can that sort of break the 1.5?
Yeah. Yeah. But it handles it pretty good. I mean, it's. You could drop in a 5th node, or you could drop in 5 nodes and partially fill them. There'd be another way to do it. The questions that we get around, well, why would you want to do something like this? And I think we're all here because I think I'm preaching to a choir of people who are interested in private deployments, private storage solutions. But the audience that we're running up into is saying, hey, I'm used to using something like Amazon or Cloud Files, sorry, Stefano. But it can be very pricey. And if you're storing this much data, 100 terabytes of data in Amazon, and you have a reasonable amount of churn, say 10% of it's going in and out of there every month, it'll be about $180,000 a year. Now, if you can get the human costs down, it's actually a pretty attractive offer to offer a product that's at parity with a public cloud infrastructure that development teams are really comfortable using. And so that's the motivation. That's the motivation. Yeah. too much, that serves as that consistent, there's a consistent hash ring. And so an object is assigned into that partition, and then that partition is allocated to a drive. And then a drive would say get, some thousand number of those partitions that object would live into, that would get moved into. It takes the location, hashes it, that goes into partition in this data structure. The data structure gives you 3 locations. Randomly pick one, and then there's on that storage node, it takes that incoming request, goes, you're in this partition, I know exactly where you're supposed to live, goes to that directory on disk, and there's a couple of tiers, as there's another structure in there with containers and counts the containers, and it looks that up on disks and reads it up and sends it back all the way. So there's one layer of abstraction that I didn't cover in that overview. Yeah, Bernard.
So I have a couple questions. One is in terms of the would that be a standard like Apache web server, or would you use a specialized web server? And the second one is this all an overlay over some kind of a Linux standard file system or something like that?
Yep.
Over the disks?
Yep.
Could you describe those two things?
So as for the web server, you would treat it, there's a web server process that is written in Python, and that's, you would think, as your application server. And then in front of that, you would put some load balancing, and that can come from off the shelf. So Rackspace uses Zeus. We've found a lot of success with Pound, and we've even done some really tricky stuff with the Arista switches to leave that out altogether and just use equal cost multi-palette writing to distribute traffic across all the proxy servers. So it's baked into Swift today. It's the application code, is how I would describe it. So it'd be the application server, kind of analogous. Yeah, it's a special purpose Python web server, and on top of that is written all the application code. And then in front of that, you can put all sorts of stuff, right? You can even go up the stack even further. For public objects, you can even stick caching in front of that, to cache popular content. And then underneath, it's an XFS file system, mostly used for some of the journaling capabilities and some metadata features underneath. But XFS. Is Arista? Oh, I don't know. If you already have Arista switches in your infrastructure, then it's free because they're already there. But there's trade-offs, right? So it depends on what you're doing, how you want it set up. If you're using something in general, think of this as the proxy servers as web servers. And if you're using something like equal cost multi-path routing, and every web server that you're using is sharing the same route, and one of them goes away, well, you have a rebalancing act that you need to do, and that's going to interrupt your streams, your TCP streams, and clients are going to have to reconnect. And web browsers aren't necessarily very good at that, but Swift clients are great at that. So what's your use case? If you are controlling your clients, then you can get away with something like that. If you're not, if you're presenting this content over the web generally, then probably not a good idea. You probably want to use a specific web server that's designed to deal with web. Yeah?
You have an existing application that they wrote for a specific request.
Mm-hmm. There's two things. So it's very similar, but it's not necessarily identical. There's a slide I had with listing a bunch of the client libraries, oftentimes what we saw is people would just swap those things out. If you're using, say, Ruby, so I have the background in that, you would use, say, a library called Fog, and you just make a very small API, Ruby API library change, and you're writing to the new data store. More fundamentally, from an architecture perspective, S3 has limitations on how many, what they call buckets you can create. I actually got a call from them once because they were yelling at me for creating too many of them. And Swift doesn't have that limitation. However, it has the converse limitation where if you have millions and millions and millions of objects in the same container, there's a performance hit. And you can kind of get around it with some hardware tweaks if you want. But architecturally, that's the difference. Swift, you can have many, 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 many containers. S3, you can only have 20. And so if you're doing something on Amazon S3 where you're creating lots of objects in a single container, you may want to flip that a little bit when you're using either Rackspace Cloud Files or Swift to take advantage of the fact that you can have lots and lots of containers. So that would be the only, those would be the major differences. Yeah. They were there at the last Design Summit, and they were one of the things that they recommended in one of the last changes that we made was changing the inode count down from 1024 down to 512, so that we could, because they were just suggesting tons of performance optimization. It was really awesome to have some of the core XFS developers in the room earlier this month who were suggesting changes that they wanted to make over the coming months.
You don't see that as a concern of using XFS as a background file system?
Versus?
Or something else. I mean, XFS, I don't know how much development is going on behind this.
I mean, I guess what are they all, theoretically it should use, it can work on any underlying file system that supports metadata. Theoretically. So you can use ext4 if you really want. There's talk of using a RAID or using a Nexena as a volume. I don't know, I still don't understand what the utility would be, but using that as the mount point instead of something like XFS. But I guess I haven't hit any of those issues as of yet. So 5 minutes, okay. So yeah, summary slide. Open source, it's good for long tail data. Complements systems. It's not a swap. It's not an either or. It's an and in many cases. Good durability, availability properties, scales to many petabytes. Yes.
Talk about when those implemented, what the sort of the pain points are when it operates. Because you started it seems like a very relatively straightforward architecture, but presumably there's some parts of it. You got to tune, you got to tweak, or
Operation tools are the biggest issue, and getting that, knowing when things are down, knowing when you're doing like rebalancing activities, understanding how the infrastructure works so you don't make any mistakes. I guess deploying, sizing the hardware appropriately from the proxy servers down to the object stores, deployment, rolling upgrades. The list goes on and on about operational duties where I think the gap is right now, and certainly that's what I'm involved in and working on how to fill that gap from this is a great core, it works great in this context, then running it at scale in production, and then how do you take that and make it so that it's an easier to install, easier to run component, and so that's the gap that I've been focusing on lately. Yeah. slides or a white paper, send me an email, joe@swiftstack.com. All right.
All right, definitely. So, thank you. Got a couple minutes in between for a break, and then we'll start up maybe about 5 minutes from now.